Hi, in this video, we want to take a look at structural equation models. Okay, so in factor analysis, we're using data that we see to try to draw inferences about variables that we can't observe directly. We call these factors or latent variables. All right, now what we want to do here with structural equation models is we want to run regression using these hidden variables, using the variables that we don't actually observe directly. Okay, so now this example that we're going to be working through is from Modern Psychometrics with R by Mayer. Here's the website if you want to get the code. Everything I've done is modified, so it's not a direct copy and paste, but I think I'm staying pretty true to the source. So factor analysis, we're working to identify and confirm variables that we cannot directly measure, our latent variables. Path analysis works to establish the direction of relationships between variables. So remember, correlation like measures the strength of the relationship between variables, but it doesn't tell us like a direction in terms of independent and dependent variables. So path analysis, all of that part of analysis is working to see, trying to determine the direction of the relationships, while structural equations extends this to the concepts of regression. All right, so for this example, we're going to be using a prejudice data set. And we have some measurements of prejudice. And we're going to use these as indicators for a general prejudice latent variable. We're going to use the agreeableness data to see, these are indicators to give us information about the latent variable about overall agreeableness, and then openness are going to be our indicators of the under the hood hidden latent variable openness personality trait. Okay. And so what we want to do, we want to take our general prejudice, our agreeableness, and our openness, and we're going to run regression. And in this example, my machine was acting a little bit wonky when I was running the code. So I went ahead and made sure that everything was clear, everything was gone before I ran it. So here I'm just making sure there's no variables from previous sessions, and I'm doing a garbage collection to clean up any memory. That's here. Then here we're saying the digits to 2, and I'm loading the data. And the data is coming from the MPsychoR package. Okay, so what we're going to do, we're going to use the indicators, these 4 indicators, to connect to a latent variable of generalized prejudice. We're going to use the agreeableness indicators to connect to an under the hood personality trait of agreeableness. We're going to use the openness indicators to give us inference about the personality trait of openness. Then what we're going to do is we're going to take the prejudice as the dependent variable, the target variable, and we're going to run regression based off of agreeableness and openness. Okay, so here, this is where we get the latent variable of generalized prejudice. This is where we get the latent variable of agreeableness. This is where we get the latent variable of openness. And this is where we're running regression. All right, so remember, when I see the equal sign tilde in the Lavon package, that means we're saying manifested by. Equal sign tilde means manifested by. The left-hand side is a factor, a latent variable. The right-hand side are observed indicators. And then when I see a single tilde, that means that it's regression. If I see a double tilde, then we're talking about covariance dependence. All right, and we're going to use the same function as always for this from the Lavon package. Lavon stands for latent variable analysis. And the model is going to be the one that we specified up here. And we're using the data set that we've already loaded, and we're going to use the MLR estimator. All right, so now let's go ahead and plot what the model looks like. And if I change these parameters, the diagram looks very different. I can have like fading and I can have different colors and whatnot to show different aspects. To be consistent with the author of the textbook, I left it the way that he put it in there. All right, so when I look here, I can see that agreeableness is a factor that is being measured by, or the agreeableness indicators are manifesting from the agreeableness factor. The openness indicators are manifesting from the openness factor. And we're saying that these 4 prejudice indicators are manifesting from the generalized prejudice factor latent variable. And we can see the relationship between these. Here are our loadings, and we can see, the connections between them using these numbers. All right. And now if we want to, we can go ahead and start looking at some hypothesis testing, rejecting the null hypothesis right there. Here, we've got our test statistic, tells us things about what we've got going on. All right, so now that we've actually got the model built, let's go ahead and let's consider some multi-group aspects. So for this first model, we're going to say that all the parameters are free to vary across the gender. So male and female can have different parameters. All right, so there's going to be more flexibility on this model than the ones that we're going to look at next. So we're going to say that the loadings can vary between genders. And now we're going to force the intercept to be equal between genders. And that's going to be done here. So with the group equal, we're going to say that for males and females, in that we're going to say that the intercepts have to be equal. But for partial, we're freeing up the restrictions on the DP, HP, and SP aspect relating to generalized prejudice. And then using the same plotting parameters, we can look to see what we've got. Now, you'll notice right off the bat is I get 2 versions of this. I'll go ahead and make this a touch smaller. I get 2 versions, one for male, one for female. And I can go through and I can check and see the difference between these throughout. Now, this is where parameters have the most freedom of all the models we're going to look at, with most freedom with respect to gender. Now, what we want to do, we're going to take the same model, but now we're going to force to have equal loadings between genders. And we're also going to put a group partial of GP manifesting off of SP. And so we can see how things have changed, throughout, if we want to start digging in and go bit by bit by bit. Okay. Now, what we want to do, we want to change it up. So previously we restricted the loadings. Now I want to restrict the regression coefficients. So previously the regression coefficients were free to be whatever they wanted between the 2 different groups. Now I'm going to let the loadings be unrestricted, but the regression coefficients have to be equal across the 2 genders. And we get our 2 diagrams once again. Now let's go ahead and compare our models. So let's go ahead and take our freedom, or our free to be anything across the genders, where we are restricting loadings and where we are restricting the regression coefficients, and take a look. And if I run ANOVA on all 3, I get free compared to regression and regression compared to loading. So we can see that from this ANOVA test, these 2 are going to be equivalent to each other. And so we would use the one that has a simpler model structure, fewer parameters estimated, which would be restricting the regression coefficients. And now here we see that there is a difference. So if I wanted to restrict one or the other, there is either loadings or regression coefficients. There is going to be a difference in terms of the informative value on the models. And so I need to make sure that I pick the right one if I'm going to use one. Now, I can also go through and start checking pairwise, and you'll notice that as you start digging in individually, you can get some results that will surprise you that are not always going to be consistent with each other. So if I check free and where with restricted loadings, there is a difference. So here, I would go with the more complicated model of the one that has free across the two groups. When I look at free compared to restricted regression coefficients, there's no statistical difference. Therefore, I would be going with the one that is simpler, that has fewer parameters to estimate. That would be with restricted regression coefficients. And then if I compare loadings and regression being restricted across the two genders, we see that there is a statistical difference. So then I need to make a choice on which one's the better one to go with. All right, so maybe you don't like this way of working through stuff. You don't like the chi-square difference test, which, I can see why you wouldn't like it. Well, one thing that we can do, let's say that instead we're more comfortable with Akaike's or Bayesian information criterions. Well, then let's go ahead and do that. So the non-nest2 package lets us compute these very nicely, and we'll actually do a confidence interval on the difference between the information criterions. There's a catch though. That catch is that we need to have maximum likelihood estimators going on. All right, so what we're going to do is we're going to take the models that we've already established, we're going to use the update function, and we're going to change the estimator to maximum likelihood. And once I do that, it's going to work out beautifully. All right, and so we do this for all three of the models. And so now let's go ahead and compare the information criterions for the model with no restrictions and the model with restricted regression coefficients. So they have to be equal across, for males and females. And so here, AIC, we notice that we have 0 in there for the difference. All right, so that confidence interval indicates that there is no statistical difference for AIC. But when I look at the Bayesian information criterion, we see that there is a difference. Okay, so now if there is we have contradictory information, we would have to make a decision on what to go with. All right, so one thing to realize is that also when we're doing subtraction off of this, we want the one that is of a lesser value. So always keep that in mind. But I look here, and here it's always positive. And here it's negative, it's between negative and positive. All right, so I have to make a choice. Which one is the criterion that I prefer to use? In general, Bayesian information criteria puts a larger penalty on term on there. So, it might be that that heavy penalty might be throwing things off. It might be that that's a better way to go. We would need to dig into the individual data and use subject matter knowledge to see what is the best course of action. All right, so now let's compare where everything is free to be whatever it wants to be with the model where we have restricted loadings. And here we see that AIC, the confidence interval contains 0. And so we see no statistical difference, but we do see a difference here. So same result or similar result as to what we had before, and we would need to dig in and make an informed decision about what's going on. Remember, with real data science, we get contradictory information if we start looking at multiple measurements. And when we get multiple measurements that contradict each other, we need to stop, double check, and make sure that we've got good solid data, good solid methodology, and we're interpreting things correctly. All right, so now let's look at the models that have different restrictions. And we can see that here the confidence interval contains 0, and here the confidence interval contains 0 both times. Okay, so here, this point of view is that the restricted loadings and restricted regression coefficients are equally fitting the model. And so which one would be the better one to work with? I don't know. I would need to start digging in and look more precisely at these models. Now, we can also use a Wrongs test for this. And something that's very nice is that this does 2 one-way tests for us. And so I know that I failed to reject the null hypothesis. I failed to reject the null hypothesis. So here we conclude that the free and restricted regression are fit equally well. Okay, so then I would go with the simpler model, the one that has fewer parameters, and that would be the one with restricted regression coefficients. Now here we see that that's a small p-value and that's a large p-value. So we conclude that model 1 fits better than model 2. All right, well, model 1 in this case is the one that has free to fit as however it wants to throughout. So we can see that that one is the better model if I'm comparing it to the loadings. And if I want to compare the two models that have restrictions on them, I see that I've got a large p-value and a small p-value. So we're going to conclude that model 2 fits better than model 1. So here, this is saying that the model that had restricted regression coefficients fit better than the model with restricted loadings. All right. And so if this was a real project that I was working on, I would use this information to decide which model is the best one to go with and proceed forward on my project. Well, that's all I've got for you. Take care and goodbye.